Yesterday we had a look at propositional equality and some basic reasoning principles to build such proofs of equality. So we saw that there's a notion of equality which is built into ACTA, which is conversion, evaluation of programs, basically. Programs with unknown variables in places. And then we have this notion which is called propositional equality. And it has one constructor that reifies this notion of equality that's internal to ACTA. So you can always prove that something is equal to itself modulo whatever notion of equality ACTA has internally. So we saw that you can prove some equalities, you can disprove others because they're clearly not true. Then we saw that this definition is arbitrary, right? All of the concepts we introduce are choices that we make because we think that this structure is interesting and worth talking about and studying. But you can always discuss your assumptions and try to relax them, for instance. And then we saw that there were some weird things. So this couldn't be proven, for instance. And finally, we saw congruence. So now I think the idea is to start proving some equalities on some defined symbols. So the first one was this one. So proving that plus 1 is the same as 1 plus. And so if you remember, so I did alt dot to jump to the definition site of the plus function my cursor was over, and it took me to the standard library saying that plus is defined by inspecting the first arguments. If it's 0, then we just return the second one. Otherwise, we pop a successor and call ourselves recursively. So if we look at the goal here, oh, I haven't zoomed in yet. So that's the row goal. But with a little bit of evaluation, we see that here the first argument is a concrete value. So plus knows that it's not 0. It is successor of something. So it can emit a successor, which you find here, and then call itself recursively on 0 plus n. And now we know that the first argument is 0. Therefore, it reduces to n. But on the left-hand side, because n is unknown, this is stuck. And no evaluation can happen. And so we just have two expressions that are different from each other. So if I introduce the n and I try to use REFL, it's telling me I don't know that n plus 1 is suck n. And even though it seems trivial to us, we need to explain to AGDA why that is the case.
Right. So yeah, this is our first instance of a game that you're going to need to learn to play. And these days I teach it to the first years. But this game is called Why Is It Stuck? Now, so we can see, we've just seen on the right-hand side, the right-hand side is not stuck. It computes the successor of n. But the left-hand side is stuck because there's an inconvenient free variable in the place that plus wants data. So no can do, we are stuck. And the way the proof always goes is to get the computation unstuck so that it simplifies. And then you're entitled to an induction hypothesis about the simpler computation, which you hope will help. Okay.
Yeah, so to get the computation unstuck, by definition, I mean, we can once again jump to plus. You can see that we need to know what the head constructor of the first argument is. We don't need to know the whole definition, just what the head constructor is. Yeah. And luckily, we can inspect it by matching on it. So earlier, we were using matching on something to do a definition by case analysis. You can similarly do a proof by case analysis saying, I want to know whether that natural number was built using 0 or a successor. Right. So in the first case, we now have 0 plus 1 is equal to 1 plus 0. And of course, everything is concrete here, so everything computes away,
Yeah.
and we just have 1 equals 1. So you can use reflexivity because now you have an equality of the form something equals itself. And then in the second case, so this is the second case originally, we've exposed the fact that the first argument is shaped successor of something. And okay, so now we are trying to prove this. And if you look at the reduced goal, so just looking at the goal, which by default will try to reduce a little bit, we can see that we were able to emit a successor here on the left and reduce the problem of adding successor of n plus 1 to adding n plus 1. Okay, so it looks like we might be able to reduce this to the problem of n plus 1 being equal to successor of n. So we can name that induction hypothesis. And here it is a justified call because n is smaller than successor of n. So the process I'm describing is indeed going to terminate at some point. I'm always referring to simpler cases. Now I can look at the goal. In the assumption, I have n plus 1 equals suc n. And the goal that I have is suc n plus 1 equals suc of suc n. Does that remind you of something, maybe, that we saw yesterday?
We've got an equation which is true, and we're doing the same thing to both sides of it. So that equation ought to stay true. We're using your actual algebra.
So we defined Kong yesterday, and we can just use Kong. So we are applying suc to both sides. So this is suc of the induction hypothesis, and that fills the goal.
Yeah.
So I've written it explicitly here to show that we are first looking at the induction hypothesis, but of course, equivalently, you could just directly write plus 1.
Yeah.
And
I mean, if you look at the goal
if you wanted.
that we got there in the step case, just doing a bit of thinking out loud, you can see once we've computed, we've got successor on both sides, and we're relieved to see that it's not some other constructor like 0. We've got matching constructors on both sides of an equation that we're trying to prove. Kong is always a good first move, because the only way two successors can be equal is if their predecessors are equal. That doesn't always go for functions that are not constructors, but for constructors, it's a no-brainer. So this is, yeah, Kong suc question mark is a good start.
So if I do Control C full stop, not this one. Which one is it?
Yeah.
I thought I was gonna.
That's
That's the one.
Mm.
So Control C full stop, I think. It tells you both the goal and also the type of the thing that you've put in the current sheds. And so you can see that here we have something that sort of matches. So then I can do Control C, Control space to feed the value that's currently in the shade and the shed and commit to it.
Yeah.
And now the question mark has been turned into a goal, and this is exactly
The induction
hypothesis. So yeah, you can think in forward deduction style, where you're calling your induction hypothesis and then trying to see how you could use it in your goal, or what we call backwards deduction style, right? You're starting from the goal and saying, okay, well, these things are the same, I'm going to remove them. These things are the same, I'm going to remove them. And eventually you arrive at something that looks like an hypothesis you could easily generate from a recursive call.
We got spurious orange.
Yes. Yeah, it's sometimes the the colors are staying around for too long. Maybe I can give you the structural proof on structural by a structural induction on the list.
Okay.
Yep.
What am I proving?
So if you remember, we defined zip width, right? Saying that if you have two lists of the same length and you have a function, you can just apply that function to each like pair of arguments that are below
I think
each
we just
other.
defined zap, but it's the same
Oh yeah.
same thing,
I don't
different
know where
day.
I don't know why they're also staggered. Like that doesn't make any sense. They should be aligned properly. Oh no, I know. Haha.
I see what you're going. Yeah.
Yeah. They were flowing like this. Yeah.
Yes.
The A1 here is flowing into here, and the B1 is flowing into. Anyways.
Yeah.
So what we want to say is that. Okay. Oh
Um,
no, it's the wrong. Boop, 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 boop. What I'd like to prove is that if both of these lists are obtained by replicating a single argument, a single value, then zipping them together is the same as replicating the result of calling the function just once. So do you want to
okay.
go?
Let's see if I can do that. I know how I want to do that, but I'm not going to. Right. So what have we got? We got we got three types, A, B, and C, and we've got a function from A to B to C, and we got A in A and B in B. And what's the statement that we want to make? Oh, yeah, and I've got to choose a length. Yeah?
Oh yeah.
Well, I'll do that here, actually, right? So we're going to say for all n in nat, if I, here I have to get this right. If I do zip width f on replicate NA and replicate NB, then that's an awful lot of hard work for nothing, because we could just have done replicate N FAB. Do I've got to do a Unicode thing, do I?
Yes. It's BN.
Yeah.
Yeah.
Right. Okay. So now I need to have a little think about how this is going to work. So replicate n makes n copies of a thing. So this program is going to work. I mean, okay, let's start by saying I've got F, I've got A, I've got B. What am I looking at? Okay, I've got an equation. I'm going to say what I typed there was Control U, Control U, Control C, Control comma, which means look at the goal, normalizing as much as possible. But, you know, here you can whistle for any computation to happen at all, right? It's completely stuck. We play, why is it stuck? And we realize that replicate is going to count stuff out. Replicate is your actual count von count. So we've got to be count von count and see what n is. N is currently not in scope. So there's a thing that Agda allows you to do these days. You say, I wish I could see n, right? Wishful thinking. Make n visible, please. It's also Control C, Control C, strangely enough. Doesn't split it. just says, it finds a way to make it visible. So now that we've made it visible, you can see it's by default hidden, but it comes straight after the B. So positionally, n in curly braces straight after the B, we're fine. Now we start looking at it. Okay, so in goal 0, that computes to nothing is nothing. Thank goodness for that. And in goal 1, we get a little bit of computation. But we see some things we like, right? Always when you're playing this game, you ask yourself, do I see things I like? And there, look, is something that looks like the left-hand side of the goal, and here is something that looks like the right-hand side of the goal, and they're not directly at the top level in the equation, but they're sitting here under conses. This is some funny Unicode double colon, isn't it?
Yes.
Marvelous. And fortunately for us, the heads are the same. So this is a job for Kong. Right. Now, I'm going to do something that looks slightly weird. I'm going to write an underscore here, and then I guess it's backslash double colon.
Yes.
Looks good. And then I'm going to write no space and another underscore. This is a thing that, oh, and a close parenthesis and a question mark. So this is a thing that we need to learn to read. Okay, so one thing that happens when you have infix operators in AGDA is that you have to put spaces between the inputs and the operators. So this thing says, haha, I've brought my own pointing device, also useful in wet weather. So this thing is the first argument to cons. There's a space here. What I'm saying is, I'm not going to tell you what it is, right? So underscore as a piece of data, you're used to it in Haskell on the left-hand side of an equation, meaning I don't care what this is. Well, guess what? In AGDA, you can use underscore anywhere, meaning I don't care what this is. What I'm saying here is, oh, you figure it out to the computer. And
yeah, on the left-hand side, it means throw it away, and on the right-hand side, it's throw it in, right?
Here there's no space, and this is, do you remember in Haskell, you could construct operator sections? So this is AGDA notation for an operator section. So what I'm saying here is, this means something cons, never mind what the something is. And there's the goal sitting there telling us what the something is. It's FAB. I know I don't have to bother typing that because it's in our face. So when I do Control-C, Control Space, that goes in the hole. And now we've got something which looks fabulously like the induction hypothesis. Let's see if Control-C, Control-A gets it. Oh, nope. Ha. That's the bizarre error message. All right, I will have to tell the thing what to do. Zip with replicate FAB, and again, it's going to pick up what number to use from the type that's already there. So there we go. Yeah. a proof by invisible induction. If I wanted for documentary purposes to be explicit that the that it was a smaller instance of the same goal, I could write the n in curly braces. And if I wanted to be fully explicit about what was being consed on the front, I can write a question mark here and then say Control-C, Control-S to solve the constraints. So that's the loud version of you figure it out. So you can just, so there's an option on the menu, or Control-C, Control-S, which means solve constraints. And that means, can you show me what goes here? And if it can't figure it out, then it will tell you it can't figure it out. But if it can, it will print it out. So the underscore just means you figure it out and don't tell me what it is, because I don't care. Alrighty?
Yeah, so auto, Control-C, Control-A is please put something in that goal. As long as it type checks, I'm happy. And Control-C, Control-S is like this should be fully determined by the constraints in the environment, and the solution should be unique. Please put it in. So they're quite different, even though it seems that they're just putting in some values in the goals.
Yeah. If you say solve constraints, you will get only forced moves, whereas if you use auto, you'll get guesswork.
Right. So that was not actually by structural induction on the list, I realized. Like,
Yeah.
This is a missed opportunity. What could we prove?
But there weren't any lists.
Yeah.
There were only the numbers.
Yes. Yeah, exactly. Maybe map compose?
Something like that.
Yeah. So let's do another one. So that this time we're talking about the lists. Oh. So what I want to say is that if I have a vector and I map a function over it, and then I map another function over it, that's two traversals, it's the same as just doing a single traversal with the composition of the two functions. So let's see if I can write that. Let's say I have G from B to C, and I have F from A to B. Then the statement is that for any vector, doing map of G on top of map of F is the same as doing map of G, F on A's.
Oh, is that all standard library stuff that we've got knocking around?
Yeah, it's standard library stuff. I'm going to need to import. That was a lower bubble.
Oh, you've got, yeah, set, yes. Okay.
Okay. So let me just jump to the definition so that we're sure we're all on board. So map is taking a function from A to B, a vector of A's, and returning a vector of B's by simply applying the function to every single element in the vector in turn. Okay. And then composition, or maybe I shouldn't do that, but
yes.
Don't look at the type. If you're composing F and G, it just means that for any input, you're returning F of G of that input. So usual composition.
Yes.
For reasons to be as general as possible, it has a very
gnarly type.
And then there's an whatever. That's not
secretly it's not composition at all.
But if we normalize, we can see that this is the usual composition we're used to. So that's good. So if I introduce all of my arguments here, so earlier Connor wanted to bring n, and so wrote n and then Control-C, Control-C. If you don't write anything in there and you do k-split, it will just introduce all of your arguments for you based on the names you've selected in the type. If you haven't given any names, they will pick horrible names for you. All right. So now we have these two sides of the equations, and we can play Connor's favorite game. Why is it stuck? So we have map on both sides. We saw that map is defined by looking at a vector, because the function we cannot inspect anyways. And depending on what constructor we have, we either return the empty one or we start building it up. So this one is stuck because A is stuck. It's just a variable. And this one is stuck because its argument is stuck, and its argument is stuck because we have A's here. So we have 2 votes for A's. So it's a good, and we have 1 vote for map F of A's. Yeah. Well, it's probably easier to match on A's than on an intermediate result like this. So I'm going to split on A's. And of course, it's not picking good names. If A's is empty, well, the map could reduce because map of F of empty is always empty. So here it did it in 1 step, here it did it in 2 steps, but we can use REFL. Okay. All right, and in the case where it's non-empty, well, it took 1 step, and this is where you see that the top level simplification doesn't go really far because it didn't even fire this thing. But it's telling me, well, on the left, I could apply F to A, and then that emitted a cons. So the outer map was able to also consume that cons, and then apply G to F applied to A. And then we have the recursive call here, which is stuck because of A's. And then on the right-hand side, well, in a single step, we applied the composite here to A, and then cons the recursive call. But if we do a lot of normalization, so UUC comma, the composition of G with F applied to A actually reduces to applying G to F of A. So we can see that we have the similar pattern now.
And this composition expands as well. Sometimes when you ask for what you want, you get more than what you want.
But we have this familiar pattern that we're really happy with, right? We have the same thing at the front, then a constructor, and then like what looks like the theorem we're trying to prove, but on a smaller thing. So here we're trying to prove it for AAs, and now it's only for A's, which means that it's actually sound to refer to that induction hypothesis, basically. So let's do the Kong. So again, here we don't care about the first argument, we just know it's there. And then the second argument is the function part. So we're computing a section. All right. And then here we have the induction hypothesis. Is it even? Oh no, okay. Yeah, it has completely given up. That's actually a good thing. Like we can import some standard library with heads, and then no one can use auto to do their coursework.
Oh, very funny.
Right, so just a reminder, so this is just the constructor alone, right? No spaces whatsoever around it. So it takes 2 arguments and returns a value. This is the left section. So second argument, no, is it the right section? I can never.
Anyway,
Whatever.
What we're saying is we're giving the tail and we're
giving the second argument.
Yeah.
This is giving the first. And this is fully applied when we have this, all of the spaces.
Yeah.
Okay.
There's one variation on this that I would be inclined to prove, which maybe I'll demonstrate if I can.
Yep.
I might discover that I can't use advanced. How do I? Oh, I can use. No. How do I select in this thing?
Shift and then the arrows, I guess.
That's what I'm trying to do.
Oh, but.
No, that's weird. Has something happened with?
Because it works on the French keyboard.
Modifier keys are different. Right, so.
So I've copied it now.
How do I? Right. Ah! It's there's a. Using other people's keyboards are hell.
No. Control Y.
No, it's a Alt V. No.
What do you want to do?
I want to paste.
Okay. Well,
Yes.
is it? Okay, I thought it was in there.
I want to just make a copy of this proof.
What the? Oh, we're in a minor mode. What? No, it's not selecting anything anymore. All right.
Right.
Oh, we're in caps lock now. Okay.
That's weird. Right. Okay. Map compose prime. So first of all, change the names. Right. Now. What? Okay, fine.
Oh, are we in insert mode?
This is not good. Yeah, we are in overwrite mode. Can I just click there to get out of it?
Maybe.
Set that, can't click. Turn off minor mode. Right. So what's going on here? Is that I've done something. So the previous proof said you can combine these two maps by composing these two functions. This says something much more useful because it says you can replace these two maps. You can replace these two maps by one map with some other function h, as long as h behaves the same as the composition on all inputs. So h is allowed not to be implemented exactly by composing G and F. It just has to behave the same way on all inputs. So this is actually most certainly useful in all the same places as map compose, but it's also useful in other places too. This is, so always be careful, you know, whenever you find yourself saying, ooh, I want this to be exactly that, sometimes that's too much. Sometimes you want it to be, oh, it's similar enough to that. Okay, now the problem is, as you can see, that I've got conses, but I've got different things left of the cons, different things right of the cons. So what am I going to do about that? Well, I might need a bit of help with cutting and pasting again. One thing you can do before you get bored. Now I can't. I'm not able to select this.
Yeah. Okay.
So I want.
What? It's not working for me either.
That's really weird. Right. Okay. So yes, one thing you can do is define this thing called Cong2, which is the same as Cong but for two input functions.
Oh. Oh, do you want to?
Yeah.
Yep.
Well, I mean, it's
switch back.
Yeah. So let's line it up nice.
you've got two things in S and a proof that they're equal. You got, I'm just going to be terrible and choose awful names. Two things in T and a proof that they're equal. And then you should know that fxa is equal to fyb. And I'm going to delete those things and say, yeah, you do the same trick everywhere you got an equation, you pattern match on REFL, then you've only got one thing instead of two. And we're home already. So now I can say Cong2 unapplied cons query. And you can see I get two goals. I get a goal for the head, which is given by applying Q to A. And I get a goal for the tail, which is just like we had before. Map compose prime G F H Q A's. Right. So that's much more useful. The standard library contains Cong2, I don't know how many.
I think we might stop at 2.
Yeah, but that's because it's been badly designed.
Oh.
Yeah. The composable thing is to say that if you have equal functions and equal inputs, then you get equal outputs. And then you can build all the Kongs instead of just the first one. Yeah.
So I think I'll show you an alternative way to do it,
Yes.
because that will be useful to make the your proofs readable. So, okay, maybe, where is it? Relation binary. Oh, it's not important. Where do we get equality from?
I don't know.
Oh,
We defined it.
From week 1. Oh.
We defined it
No,
in this file.
Oh.
That's
Oh,
the
yeah, we
short list.
did. Oh.
So we've got no library.
I see.
We have to do it all ourselves.
Oh, that's very unfortunate. You know what? Let's do it like that. So let's keep this around then.
Yeah.
So that's a valid proof. And then, yeah, it is. I'm just gonna
Start anew.
it got into a weird state. So
Yeah. Okay.
right. So let's do the proper thing then. Quality renaming. So here we have something that we define that clashes with the standard library. So in the imports, you can just rename it on the fly. And then I'm gonna want to use this rezoning, if I can spell it, and Kong. Oh, okay. So now I want to state exactly the same thing, but using the equality from the standard library. Up. And so, no. The definitions are going to be clashing, so Kong to Kong prime.
Yeah, it's hilarious.
And using, I want to keep using REFL. So REFL is a constructor, so we're fine.
Yes.
Up.
Right. Yeah. Okay, back in the
Okay. So now I'm using the equality from the standard library. The base case is still the same. The step case is also still the same. But I'm going to now use the equality reasoning module. So if you jump to its definition, it's a bit complicated. There's lots of like, whatever, it doesn't matter. What matters is that you can just open it. So you can open equality reasoning. Right. And then you have access to a nice syntax to write a a bunch of equalities that follow each other so that you can flow from the left-hand side of your equation all the way to the right-hand side. But each step of the way, you're recording both the transformation you're performing on the goal and also the reason why they're valid. So you would typically say begin, which I always spell begin, being. And then you have a step. And then you will get somewhere else. So this is the standard pattern these things have. And then I typically just copy paste a bunch of steps because it's going to take more than one step to get there. So now I've built this thing. I can use Control-C, Control-S, and I will fill in the bits that are known, and then it's my job to go from one side to the other. So here you can see I have map over a constructor. This can reduce. So I have steps that are free. So the justification here is just empty because I'm doing it by computation. So now here, if I do Control-U, Control-U, Control-C, Control-S,
Yes.
I'm telling it, please compute the normal form of this. And it's reduced G applied to F to A on top of map G, map F of A's. So this step is free. I don't know why I'm getting so much yellow, but it will be gone by the end.
Yes. You want to do the same thing at the other end, of course.
Oh yeah, that's true. This is also stuck, but well, it's not stuck, but it's not showing the reduced form. So I know I can do a little bit of free work here. All right. So now I need to find a way to go from this side to that side. So I could either first transform this bit or that bit. Let's start with the leftmost one. So I can say here I'm using congruence over this is the one I want. So there's no space here before the constructor. And I'm saying the tail, you figure it out. It's easy anyways. Okay. Oh, Kong prime. So different equality, right?
Yeah.
I just had to rename it because of the import. And so now I have to...
Yeah, why not write the actual term you're trying to get to?
Oh,
Yeah.
well, I quite like to use
Get it.
solving. Like,
Yeah.
okay, this one doesn't know yet. What about this one? No. So I want to take a step, right, from G of F of A to H of A so that I have matching H of A's here. And then the tail, can it not figure out what the tail should be?
No, you
Okay.
haven't. You have to fill in goal 4 first. That's,
Okay, so now it's telling me, well, I'm happy for you to go from that step to the other if only you can prove that they are equal. And luckily, we have this Q hypothesis. Oops. That tells us what it is. Okay. And then here, it's just going to be the same thing over again. Okay. So now I've taken a step by modifying the head of the list, of the vector. It's matching my goal, so I'm not going to do any more work here. The tail, however, is still different. So I can use another Kong, and this time acting on the tail. So I'm saying whatever the head, I'm going to be modifying the tail. So it's telling me, okay, as long as you can take a step to something, I'm willing to entertain your idea. Okay. Let's keep this one. Well, actually, we're going to jump directly to this, right?
yeah.
So I had one too many steps. So now, finally, to bridge the last gap, I need to go from map G, map F to map H, and this is the induction hypothesis. So this is my compose prime prime. G, F, H, Q, A's. Yes.
Mm-hmm.
So this, for longer proofs where you're taking multiple steps, it's just easier to write it using this kind of
Yeah.
syntax, just like you would on paper, basically, where you're
Can we
slowly...
get both versions on the same
Yeah.
screen at the same time?
Oop.
Yeah. Or thereabouts. That's good enough, I think.
Yeah.
Right. So, I mean, a big part of the problem in Agda sometimes when you're doing proofs is that they become not very readable. So Like, what's important here is the type of this thing, right? We figured out these things by looking at the goals, but the goals evaporate once you finish the job. They don't end up in the document. And the document you end up with is sometimes extremely opaque. And I think this is an example of a proof that is unreadable. I mean, you could maybe guess, okay, yes, something structural is going on here. Whereas this proof, we're crucially recording which things were equal to which other things, as well as why. And now we can actually read this as an explanation much more clearly than this thing. So even though they're doing the same job, one of them you would go back to a few weeks later and think, yeah, that makes sense. Whereas the other one is essentially write-only code. And the way you would make sense of it is actually to comment it out and fill it back in again a little bit at a time to see what was going on in the goal buffer. And that is, that's an important part of how you do AGDA program comprehension, is actually rebuilding it gradually to see what's going on. And that's some criticism of the language.
Mm.
If that's what you have to do to read the program, is to write it again, something's no right.
So I think we'll jump right to the end. We had an example of an annoying type, but this is something you actually mentioned yesterday. It's the fact that we implemented Kong, but that's not the intrinsic, like what actually defines what it means for two values to be equal. The actual sort of profound meaning of equality is that two things that are equal cannot be distinguished from each other. And this is typically known as Leibniz law, or the indiscernibility. Okay, I'm not going to try to say it. And how can you formulate this? Well, you can formulate this by saying, I have a function which will witness this. And it's saying that if I have not only a set, but also predicates on that set. So predicates can be understood as a family of sets indexed by values in that set, because you can say, well, P is true of this value in A, but P is not true of that other value in A, and so on.
Yeah, so something that's talking about A, or it's just talking about a value in A.
And then what it means to have Leibniz law is to say that if you have two values in A and they are equal, then if you can prove that P holds of X, then P should hold of Y. And actually, I should maybe, okay, this is annoying. I mean, morally what we're saying, but this is not the type of subs in the standard library, so I don't know if it's good to say it like this, but
yeah,
it's more something like this, right?
Yeah.
What does it mean for X to be equal to Y? Well, it means that for any observation we can make of P of X as a predicate, if it holds, then it also holds of Y, meaning there's no way for us to distinguish X from Y. And the implementation you may expect is really easy, because when we match on REFL, X becomes Y, and so a proof of P of X literally becomes a proof of P of Y. So we can just reuse it and return it immediately.
Yeah, so this over half a millennium between Al-Khwarizmi, principle of balancing, take a true equation, do the same thing to both sides, still true, and Leibniz saying, hang on a minute, we really want to talk not just about which equations are true, we want to talk about all properties of stuff, and things are equal if they have the same properties. And yes, it is a funny thing that it's odd that there's an asymmetry here, right? This is nice and symmetrical, but it's like, why are we saying, oh, if you've got P of X, you get P of Y? What about the other way around? Exercise for reader. It turns out that this in particular is enough to show that if x equals y, then y equals x. And then you could plug that in here and get this arrow to go backwards.
And it's extremely powerful, right? Because it's quantifier over all possible p's. You get to pick the p you want. And so if you're creative enough in your choice of p, you can prove an awful lot of stuff.
Yeah. So you should think of P here as not something you invent. You should think of it as the problem at hand. I've got a problem, it talks about y, and I want it to talk about x because I know x is y. Here's a problem simplification step I can make to reduce my problem that talks about y to the same problem but talking about x. Read the type backwards and exploit the fact that you're abstracting over the return type to say, oh yeah, I can use this to solve all sorts of problems. All right.